This is the Antonov An-225 Mriya, the world's largest aircraft until 2022. A six-engine strategic airlifter so massive that it dwarfs every other plane ever constructed, including the aircraft it was designed to carry on its back. Stand next to it on the tarmac and you can't see both ends at once. The aircraft stretches 275 feet from nose to tail, longer than the wingspan of a Boeing 747, and it's simply too big to take in from ground level. And that size exists for one reason: to carry things that won't fit inside anything else. The wings tell you immediately this isn't a normal airplane. They stretch 290 feet tip to tip, wider than the American football field, including both end zones. Wings that massive exist because the aircraft weighs 1.4 million pounds fully loaded. To put that in perspective, that's roughly 160 average cars stacked into a single machine and asked to fly. Getting that weight airborne requires lift that no smaller wing can generate. So the An-225 carries nearly a quarter acre of wing surface, 9,740 square feet of aluminum alloy designed to grip the air hard enough to hold the impossible aloft. But giant wings create their own problems. Those wingtips extended 145 feet from the cockpit in each direction, far beyond what any pilot can see from the flight deck. So the pilots sit in a cockpit positioned high on the nose, giving them sight lines down to the taxiway edges during ground operations. Even then, it's not enough. Wing walkers, human guides on the ground, escort the aircraft whenever it moves near terminal buildings, watching margins that no camera system can fully capture. The tail creates another challenge. A conventional airliner has a single vertical stabilizer, that tail fin at the back that keeps the aircraft pointed straight. But the An-225 was designed to carry cargo on its back too, and a single tail would be blocked by cargo mounted on the fuselage spine. The solution? Twin vertical stabilizers rising 60 feet above the tarmac, 6 stories tall, mounted at the tips of the horizontal tail. They stand clear of anything mounted between them, providing control authority no matter what's riding on top. 6 engines hang from the pylons beneath the wings, 3 per side. Each Ivchenko Progress D18T turbofan produces 51,600 pounds of thrust, roughly the same as a single engine on a Boeing 777. Combined output from all 6, 309,600 pounds of force. A Boeing 747 produces 266,000 pounds from 4 engines. An An-225 produces 16% more power and needs every bit of it because of something called the bypass ratio. When air enters the front of the engine, most of it never gets burned at all. About 85% just gets shoved out the back by a giant fan. Think of it as a 7.5-foot diameter room fan spinning at thousands of RPM inside a tube. Only 15% of the incoming air actually goes into the hot section where the fuel burns. That cold air blowing past the core produces most of the thrust. Engineers call this the bypass ratio. How much air goes around the engine versus through it. High bypass means enormous thrust with manageable fuel consumption. It's the difference between a blowtorch and a leaf blower. And for lifting impossible weights, you want the leaf blower. The 15% that does enter the core gets squeezed through 14 compressor stages until it reaches 24 times the normal atmospheric pressure. Imagine the crushing force 800 feet underwater, but with air. That compressed air mixes with jet fuel and ignites at 2,900 degrees Fahrenheit. The expanding gases spin turbines that drive the massive fan up front, completing the cycle. 6 of these engines working together produce enough force to accelerate a small apartment building to flight speed. That kind of power demands fuel. The tanks hold 96,000 gallons, enough to fill nearly 5 average swimming pools. At cruise, the 6 engines drink 4,200 gallons per hour. That's enough to fill 280 car gas tanks every 60 minutes. Just gone. The massive capacity buys 18 hours of flight time and 8,300 miles of range when lightly loaded. But fill the cargo hold to maximum and that range drops to 2,160 miles. Still enough to cross continents, but demanding fuel stops for intercontinental missions. Every pound of cargo trades directly against range. That equation defines every AN-225 mission before it launched, and surprisingly, this thing has been around for decades. The aircraft exists because of the Buran program. In the early 1980s, the Soviet Union was building its own space shuttle and needed a way to transport completed orbiters from manufacturing facilities to the Baikonur launch site. The existing AN-124, itself the largest military transport in the world, couldn't carry Buran externally. So Antonov took the AN-124 as a starting point and stretched everything. The fuselage grew 23 feet longer. The wingspan expanded by 49 feet. 2 engines became 6. The result first flew in December of 1988, and 3 months later carried the Buran on its back to the Paris Air Show, creating one of the most iconic photographs in aviation history. But carrying a space shuttle on its back, as historic as that was, only hints at what makes this aircraft truly extraordinary. The real capability lies inside. An AN-225's cargo hold is the largest enclosed space ever designed to fly. Internal dimensions are 142 feet long, 21 feet wide, and 14 feet tall. That's a pressurized tunnel longer than a 737 fuselage and wide enough to drive a delivery truck through. Total volume, 45,900 cubic feet, enough to swallow 16 standard 40-foot shipping containers arranged in 2 rows of 8. This hold exists because some things can't travel any other way. Power plant generators weighing 150 tons, industrial turbines too large for rail tunnels, emergency relief supplies that would take a fleet of smaller aircraft to move. When something absolutely must fly and nothing else can carry it, the AN-225 got the call. Loading cargo this large requires opening the aircraft like a clamshell. The entire nose section hinges upward on hydraulic actuators powerful enough to lift a small building. Ground crews connect external power, verify hydraulic pressure, and initiate the sequence. 10 minutes later, the nose towers above the tarmac. The full 21 by 14-foot cargo bay cross-section gaping open to the world. From a distance, it looks like the aircraft is yawning. Up close, it looks like a gate into another dimension. A tunnel wide enough to swallow a house. But here's the problem. How do you move a 100-ton generator into a space like that? You can't just drive it in. The answer lies here. 2 parallel rail tracks run the entire 142-foot length of the hold, mounted flush with the deck. Roller bearings built into the rails reduce friction to almost nothing. Between the rails, the floor hides something remarkable. Thousands of steel balls recessed into the surface, each one free to rotate in any direction. Place a 150-ton turbine on this floor, and something almost magical happens. It glides. 2 loadmasters pushing with their shoulders can slide cargo that would take a crane to budge on any normal surface. Need to shift a generator 6 inches left to clear a fuselage frame? Just push it. The balls rotate beneath the load. Friction vanishes. And equipment heavier than a locomotive moves at walking pace. One more system makes loading possible. Rolling a 200-ton generator up a steep ramp invites disaster. The load wants to roll backward. Winches strain against physics, and one slip cable could crush everyone nearby. The kneeling system eliminates that problem. Hydraulic actuators compress the nose gear while extending the main gear, tilting the entire aircraft nose down, like a dog lowering its head to eat. The cargo floor drops closer to ground level, the ramp angle flattens, and suddenly that 200-ton generator rolls onto the hold on near level ground. The sequence takes 5 minutes and transforms an impossible task into merely a difficult one. Of course, you just can't throw cargo in here and expect the aircraft to cooperate. Weight distribution matters more than almost anything else in aviation, including the AN-225. Every surface of the hold, floor, walls, ceiling, features load restraint hardpoints rated for tens of thousands of pounds of tension. Chains, straps, and tie-down nets secure each item against forces that would turn unsecured cargo into a 50-ton missile. This is important because if a heavy load shifts during flight, It changes where the aircraft's weight is centered. Pilots call this center of gravity, and every aircraft has a narrow range where it must stay. Move the center of gravity too far forward and the nose drops uncontrollably. Too far aft and the nose pitches up until the aircraft stalls. A single unsecured load sliding during turbulence can push that balance point outside the safe range in seconds. The loadmasters who plan An-225 missions spend hours calculating weight distribution, running the numbers twice, checking them again. Getting it wrong isn't an option. Maximum internal payload reaches 551,000 pounds, more than twice what a C-5 Galaxy can carry. And the Galaxy is America's largest military transport. But the An-225 can also haul cargo externally. That reinforced spine, designed for Buran, accepts oversized loads on external pylons. Theoretical combined maximum, 551,000 pounds inside, plus 440,000 pounds on top. But no mission has ever tested those limits together. Even though this has never been attempted, one thing is for sure: the wings can definitely handle it thanks to some ingenious engineering. The wing shape is specially designed to cheat the sound barrier. This is because as aircraft approach the speed of sound, even well below it, air flowing under the curved upper surface of the wing can actually accelerate past Mach 1, creating miniature shock waves. Those shock waves produce enormous drag that fights against forward motion. An An-225's wings use what engineers call a supercritical airfoil, a shape specifically sculpted to delay this effect, keeping airflow smooth at cruise speeds around 500 miles per hour. Without this careful shaping, the aircraft would burn significantly more fuel fighting turbulence of its own creation. The leading edge, the front of the wing, incorporates full-span slats. These are movable surfaces that extend toward and down during takeoff and landing, increasing the wing's curvature. A more curved wing grips the air better at slow speeds, which matters enormously when you're trying to get 1.4 million pounds off the ground. The trailing edge features enormous Fowler flaps that extend backward and down. Unlike simple flaps that just pivot, Fowler flaps actually increase the wing's total area while also adding curvature. It's like the wing grows bigger when you need it most. With slats and flaps fully deployed, an An-225 can stay airborne at speeds that would drop a clean wing aircraft out of the sky. The flight controls scale to match the aircraft. Each aileron, the surfaces near the wingtips that control rolling, measures over 26 feet long, bigger than many small airplanes. Moving surfaces that large against the force of 500-mile-per-hour airflow would be impossible with human strength alone, so hydraulic systems do the work. Those systems operate at 3,000 pounds per square inch, about 100 times the pressure in your car tires, enough force to cut through steel if a line ruptures. The aircraft runs triple redundant hydraulics because losing control of surfaces this large means losing the aircraft. Two complete systems can fail, and the An-225 still flies home. Now for the landing gear, which exists in its current form only because concrete has limits. A 1.4 million-pound aircraft concentrating its weight on a few wheels would punch through most runway surfaces like stiletto heels through wet cardboard. The solution? 32 wheels. 28 main gear wheels arranged in 2 rows of 7 on each side of the fuselage, plus 4 nose wheels up front. That's more wheels than most regional jets have passengers. The configuration spreads weight across such a large footprint that ground pressure actually measures lower than some aircraft's half its size. Runways that would crack under a more concentrated load barely notice the An-225 rolling across them. But spreading weight is only half the problem. Runways aren't perfectly smooth, and at this weight, even small bumps transmit enormous forces into the airframe. Each main gear leg uses something called oleo-pneumatic shock absorbers, essentially nitrogen gas compressed over hydraulic fluid. When a wheel hits a bump, the strut compresses up to 16 inches, absorbing the impact instead of transitioning it to the fuselage. The struts don't just handle landing impacts, they isolate the aircraft from thousands of small jolts during every taxi. And the An-225 has shown time and again how it makes the impossible look ordinary. On May 13, 1989, the An-225 prepares for a flight that will demonstrate capabilities no other aircraft can match. Mounted on its spine, the Buran space shuttle, 118 feet long, weighing 137,000 pounds. Combined weight at brake release, 1.23 million pounds of aerospace hardware about to attempt sustained flight. The takeoff roll begins at Baikonur Cosmodrome in Kazakhstan. 6 engines spool to takeoff thrust, the sound building from a whine to a thunder that shakes the ground for miles. Combined output, 309,600 pounds of force. The acceleration isn't extreme. At this weight, even that much thrust produces a gradual push, but it's relentless. The aircraft begins moving and keeps building speed. At 161 miles per hour, something changes in the feel of the controls. The wings are biting now, generating enough lift to partially unload the landing gear. The pilots sense it through the yoke, lighter pressure, more responsive. The wheels are still spinning on concrete, but they're carrying less weight with every knot of airspeed gained. The wheels leave the runway at 7,200 feet from brake release, over a mile of concrete consumed before the aircraft becomes airborne. The An-225 climbs slowly, trading speed for altitude at about 1,000 feet per minute. With Buran mounted high on the fuselage, the center of gravity sits higher than normal, requiring constant adjustments to maintain stable flight. Cruise altitude settles at 20,000 feet, lower than typical because the shuttle's external drag penalty limits efficient altitude. Cruise speed drops to 400 miles per hour. The flight covers 2,800 miles with fuel stops, demonstrating that the An-225 can transport orbiters across continental distances. Standard missions follow similar procedures with less dramatic cargo. Industrial turbines, generators, humanitarian supplies, all loaded through the nose, secured against the forces of flight, and delivered to runways long enough to handle the weight. The An-225 requires at least 10,000 feet for maximum weight operations, limiting which airports can accept it. Every mission begins with the math: payload weight, fuel required, runway available. The numbers must close before the engines start. And even as the aircraft gets airborne, the pilots are already planning how to land hours before final descent. The crew calculates approach speed, fuel reserves, and runway requirements based on landing weight. Each varies by hundreds of tons depending on payload and remaining fuel. Approach speed at maximum weight, 161 miles per hour. The slats and flaps deploy progressively during descent, reconfiguring the wing for maximum lift at minimum speed. The aircraft's nose pitches up and flaps extend, requiring constant trim adjustment to maintain the glide path. On short final, the An-225 presents an image that defies physics. An aircraft the size of a small building, hanging in the air at 160 miles per hour, descending toward concrete at 200 feet per minute. 6 engines idle at flight power, ready for instant response if something goes wrong. Touchdown occurs at 155 miles per hour. The 28 main wheels contact first. Their oleo struts compress smoothly as 400-plus tons transfers from wings to ground. The nose gear lowers immediately after, providing steering for rollout. Stopping combines 3 systems. Thrust reversers deploy on all 6 engines, redirecting exhaust forward. The same engines that accelerated the aircraft now work to slow it down. The massive flaps stay extended, creating drag that scrubs speed. Wheel brakes pulse through the anti-skid system, preventing lockup on the runway surface. Total stopping distance, 6,000 feet from touchdown to taxi speed. After the Soviet Union collapsed, the An-225 found new purpose. Antonov Airlines operates it as a charter-heavy lift transport, hauling oversized cargo that nothing else can accommodate. The aircraft holds records that still stand today. Heaviest single item ever airlifted, 247 tons. Heaviest total payload, 253.8 tons. Longest cargo piece, 138 feet. And then, on February 24, 2022, everything changed. The An-225 sat at Antonov Airport in Hostomel, Ukraine, undergoing engine maintenance. Russian forces attacked the airport in the opening hours of the invasion, seeking to establish an airborne bridgehead near Kiev. Ukrainian defenders held the airport through desperate fighting, but the An-225 burned in its hangar. Antonov confirmed the destruction on February 27, 2022. The airframe had flown for 33 years, set records no other aircraft could approach, and carried cargoes that literally could not move any other way. Gone. An incomplete second airframe still exists, 70% finished. Completing it would cost over $800 million, and the industrial base that built the original no longer exists. Some components would need to be manufactured from scratch. Some expertise has been lost to retirement and war. The Mriya, Ukrainian for dream, flew for 33 years as proof that engineering could achieve things no one else attempted. Its destruction proved that some things, once lost, cannot be rebuilt. Bye for now.